Hi and welcome back to my channel. Today we're going to be looking at the Section 1 multiple choice of the 2019 paper for Advanced Higher. Let's have a look at question 1. In an emission spectrum of mercury, the line at 310 nanometers is due to what? So the statements relate to different parts of the electromagnetic spectrum and whether or not light is being absorbed or released. The first thing to consider is which part of the electromagnetic spectrum does this wavelength relate to. 310 nanometers is within the ultraviolet region of the electromagnetic spectrum. The visible region of the electromagnetic spectrum would be between 400 and 700 nanometers. Because this is in the ultraviolet, we can discount C and D. We now need to decide if the energy is being absorbed or being released. In an emission spectrum, the electrons are promoted to higher energy levels, and then when they fall back down again, they release energy, which is what we see as light. This leads us to B as our answer. Question 2. In which of the following changes would heating to constant mass allow the mass of water produced to be determined? When you're heating to constant mass, you're taking your solid product and you're weighing it, heating it, allowing it to cool in a desiccator, and then re-weighing. You repeat this cycle until the mass does not change. To find the mass of water, you would be heating up a product which has water attached to drive off the water, but that substance itself must be solid. The only equation here with a solid involved is D. Question 3. Which of the following reagents would be most suitable for the gravimetric determination of magnesium ions in water? For gravimetric determination, we require a solid. This is because gravimetric determination is about weighing masses. If this is the case, then we need to produce a precipitate when we mix one of these solutions with the magnesium ions that are in water. The solution itself needs to be soluble so that we can form that precipitate. Using the databook, we can find that silver carbonate is not soluble. We would then need to look at the substances that would form when we mix these together. If you were to mix sodium nitrate with magnesium ions, you would get a sodium solution and magnesium nitrate. Magnesium nitrate would be soluble. If you were to mix silver nitrate, you would get a silver solution and magnesium nitrate, which would be soluble. On mixing sodium carbonate, you would get a sodium solution and magnesium carbonate, which is insoluble, and you could then weigh this. Question 4. Hundt's rule states that A. Electrons occupy degenerate orbitals singly with parallel spins before pairing. B. No two electrons in an atom can have the same set of 4 quantum numbers. C. Electrons occupy orbitals in order of increasing energy. Or D. The energy of an electron in an atom is quantized. Hundt's rule is about having maximum multiplicity. This means that electrons will go into orbitals with parallel spins singly before they'll start to pair up. Question 5. Which of the following molecules contains the smallest bond angle? To work this out, we need to know what shape each of these would be. To do this, we use the VSEPR rules. Here we have beryllium chloride. Beryllium has 2 electrons and we add 2 for the 2 chlorines. We would then take away any charge. We have no charge here. This gives us 4, which we then divide by 2 to get number of electron pairs. So we have 2 electron pairs with no lone pairs. This means that this would be in a linear shape. If we look at BCl3, we have 3 electrons on the boron plus 3 chlorines to give 6. We then divide by 2 to find the number of electron pairs, which is 3, and there are no lone pairs on this one. This means we would have a trigonal planar arrangement. For CCl4, we'd have 4 electrons on the carbon plus 4 chlorines to give 8, divided by 2 will be 4 electron pairs with no lone pairs. This gives a tetrahedral arrangement. And then finally PCl5. We have 5 electrons on the phosphorus plus 5 chlorines attached to give 10, divided by 2 to have 5 electron pairs. This means that we'll have a trigonal bipyramid arrangement. In the BeCl2, we have a 180 degree bond angle. In BCl3, we have a 120 degree bond angle. In a tetrahedral arrangement, we have a 109.5 degree bond angle. And in a trigonal bipyramid, we have two bond angles. We have a 90 degree bond angle here, but we also have a 120 degree bond angle here. This means that PCl5 will have the smallest bond angle. Question 6. Iron forms both Fe2+ and Fe3+ ions. Which of the following statements is correct? So here we're looking at the electron arrangements of Fe2+ and Fe3+. Fe2+ will have the arrangement of 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. Whereas Fe3+ will have the arrangement 1s2, 2s2, 2p6, 3s2, 3p6, and 3d5. If we take each of the examples in turn, we can see that A, Fe2+ ions have more occupied energy levels than Fe3+ ions. They each have the same number of occupied energy levels. For part B, Fe2+ ions have more unpaired electrons than Fe3+ ions. In an Fe2+ ion, we would have this arrangement for the d electrons, where we have 4 unpaired electrons. In an Fe3+, we will have 5 unpaired electrons. Fe3+ ions are a better reducing agent than Fe2+ ions. To be a reducing agent, then the ion needs to be able to be oxidized. Fe3+ was not oxidized any further, whereas Fe2+ can be oxidized further to Fe3+, meaning Fe2+ would be a better reducing agent. Fe3+ ions are more stable than Fe2+ ions. They are more stable because of this arrangement where we have a half-filled d subshell. Question 7. Which metal in the following ions has the highest oxidation state? If we take each in turn, we can work out the oxidation states. Here we have 7 oxygens which each have a charge of 2-, which is -14. Overall, this ion has a 2- charge. This means that the 2 chromiums together must be worth +12, and each of those must be +6. For a permanganate ion, you have the 4 oxygens at -2, which is -8 overall. The overall charge of the ion is -1, which means that the manganese must be +7. In VO2+, you have oxygen, which is 2-. Overall, we have a 2+ charge, which means the vanadium must be +4. And then finally, you have tin 4+. This is the oxidation state of the tin. This means that permanganate has the highest oxidation state for the metal. Question 8. The copper complex shown can be used as a green food colouring. Which line in the table is correct for this complex? So here we're looking at coordination number of the copper and the classification of the ligand. The coordination number of the copper is how many bonds are to the copper. So we have 1, 2, 3, 4. So the copper is forming 4 bonds, so we can ignore A and B. The classification of the ligand is how many bonds the ligand itself is making. So we can see that this ligand is bonding through these 4 nitrogen atoms, and that means that this ligand is tetradentate, leaving D as our answer. Question 9. Which of the following changes will cause the equilibrium constant to increase? So the only thing which can change the equilibrium constant is temperature. So we can ignore C and D. And we need to have a look at if decreasing or increasing the temperature will cause the equilibrium constant to change. The equilibrium constant is given by the equation K, concentration of the products, in this case Y, divided by concentration of the reactants, in this case X, to the power of 2. To increase the value of K, we need to increase the concentration of the products, which means we need to shift the equilibrium to the right. This is an exothermic reaction, therefore this reaction will give out heat. To force this reaction to the right and therefore produce more products, we need to decrease the temperature. Question 10. The following graph shows the variation in delta G with temperature for a reaction. Which of the statements is true? We're looking at the feasibility of this reaction. Reactions are feasible when delta G is less than or equal to 0. This means that we need to have a look at where the line crosses the 0. So the line crosses at this point here, and anything below this line here is going to be feasible. This means that for all of the temperatures above this point, the reaction will be feasible. And this point is at 300 K. So the reaction is feasible above 300 Kelvin. Question 11. Iron 3 oxide can be reduced to iron using hydrogen. Calculate the enthalpy change for the reduction of iron 3 oxide using hydrogen. So to do this, we have delta H equals the sum of delta H formation of the products minus the sum of delta H formation of the reactants. So for our products we have iron, which is 0, plus water, which is negative 242. Now we need to multiply that by 3 because there's 3 in the balanced equation. And then we look at the reactants. The reactants are iron oxide, which is negative 822, and then hydrogen, which is 0. So here we have negative 726 minus negative 822, which equals positive 96. Question 12. Which line in the table is correct for water condensing? To do this, let's think about what is happening during water condensing. We are taking water as a gas and changing that to be water as a liquid. If we deal first with the entropy, we are going from a disordered system of water as a gas to a more ordered system of water as a liquid, which means that your entropy will be negative because it's falling. So we can ignore C and D. As you go from water as a gas to water as a liquid, the system is losing energy. Therefore, this is a negative enthalpy change, giving B as our answer. Question 13. The results in the table were obtained for the reaction X plus 2Y to give Z. For these results, the rate equation is what? So here we need to look at the concentrations of the reactants and the effect that it has on the initial rate. If we look at experiment 1 and 2, we can see that the concentration of Y does not change, but the concentration of X is doubled. If we then look at what happens to the rate, we can see that the rate is also doubled. This means that for X, we'll have order 1. If we look now at experiment 1 and 3, we can see the concentration of X doesn't change, but the concentration of Y doubles between 3 and 1. If we have a look at the rate, we can see that it doesn't change. This means that for Y, the order of reaction is 0. Therefore, the correct answer is A. Rate equals K multiplied by the concentration of X. Question 14. The rate of a chemical reaction is second order overall. The units for the rate constant K are what? So for this, I'm going to write out an equation for a second order reaction. So the rate of reaction is going to be in moles per litre per second, as we can see that those are the units that we have within our options. The concentration is always given as moles per litre. Now we need all of the units to cancel by the end. So we can see that we have a moles per litre on each side of the equation, so I'm going to cancel one of those. I don't have anything to do with seconds on the right hand side, so we can pull that over and we know that'll be part of our units for K. We're then left with this moles per litre for the concentration. Now we need this to be part of the units of K, but we need to invert it so that it will cancel out, which means that we will have per mole litres per second. We then need to find this within the answers. It may be written in a different order, and we can see that that is answer B. Question 15. The structure of 2-furanitrile is shown. The number of pi bonds in 2-furanitrile is what? So pi bonds form when you have multiple bonds. We can see that we have 2 carbon-to-carbon double bonds. For each of those, they will have 1 sigma bond and 1 pi bond. So here are 2 pi bonds that we might have. We then have a triple bond between carbon and nitrogen. One of those bonds is a sigma bond, and the other 2 are pi bonds. This means we have 4 pi bonds in this structure. Question 16. The structure of one form of vitamin B3 is shown. The molecular formula for the structure is what? So for this we need to understand skeletal formula. At each of the corners you have a carbon, and you also have enough hydrogens to make up the valency of 4. So it's best to go around and draw in the hydrogens so that you can see where they would be. We then need to count up all of the different atoms within this, starting with the carbons. We have 1, 2, 3, 4, 5, 6. We have 6 carbons in this structure, so you can ignore C and D. Then have a look at the hydrogens. We have 1, 2, 3, 4, 5, which should lead us to A, and let's check with the oxygens. We have 2 oxygens and 1 nitrogen. So A is the molecular formula for this structure. Question 17. Which of the following compounds exhibits geometric isomerism? Geometric isomerism happens when you have a carbon-to-carbon double bond with different groups on either end of that carbon-to-carbon double bond. If we have a look at A, we can see that at this end of the carbon-to-carbon double bond, we have an H, and then we have this carbon group here. On this end, we have 2 H's, which means that we don't have anything which can go on either side of the double bond. In B, we can see that at this end we have a methyl group and a hydrogen, whereas at this side we have 2 methyl groups. So there's no difference in symmetry here. So this one also will not have geometric isomerism. For this one, we have a hydrogen and the ethyl group, and a hydrogen and a methyl group. This means we have different groups on either end of the carbon-to-carbon double bond, which could either be on the same side or different sides of the double bond. C has geometric isomerism. Question 18. The systematic name of this molecule is what? So here we have to have a look at what we have in the structure. We have 1, 2, 3, 4, 5, 6 carbons in our longest chain here. Now if we number them from the end closest to the double bond, it is symmetrical, so we can just number from the left here. So this is going to be based on hex 3ene, so we can ignore A and B. We can see that we have our dimethyl group, we've got a methyl on H3 and 4, and they are on the same side of the double bond. This means that this is the cis isomer. Question 19. The structures shown below are isomeric amines. Which line in the table is correct for trimethylamine when compared to ethylmethylamine? So what we have here, trimethylamine, is a tertiary amine, whereas ethylmethylamine is a secondary amine. Because this is a secondary amine, it has an NH bond which allows it to hydrogen bond with itself or to water. If we have a look at the boiling point for a secondary amine will be higher, which means that the trimethylamine will have a lower boiling point. So we can ignore A and B. The secondary amine will also be more soluble in water, which means that the tertiary amine is less soluble in water, which means that this answer will be D. Question 20. The reaction of butanone with lithium aluminium hydride produces what? This relies on you knowing what lithium aluminium hydride does. Lithium aluminium hydride is a reducing agent, which means that we'll take the structure of butanone back to its alcohol that it started from. Butanone has this structure, which if reduced will take us back to this alcohol, which is butan-2-ol. Question 21. Which line in the table is correct for the types of reaction taking place at steps 1, 2 and 3? So we're starting off here with benzene and we're producing nitrobenzene. This reaction going from benzene to nitrobenzene is an electrophilic substitution called nitration. So we can ignore A and D as we're looking for electrophilic substitution in step 1. In step 2, we're taking nitrobenzene, the NO2 part, and we're turning this into phenylamine. So we're taking the nitro part and we're reducing this back to NH2, which means that we should be looking for C, which we can confirm by looking at step 3. By looking at step 3, we can see we're taking an amino group and we're forming an amide. So this is a condensation reaction, much like would happen if you were making a protein. This confirms that C is the answer. Question 22. Carboxylic acids can be prepared in different ways. Which of the following is a suitable method for preparing a carboxylic acid in one reaction? If you were to try and make a carboxylic acid by addition to an alkene, you would not be able to go all the way to making a carboxylic acid. You would be able to add something across the double bond, but then you would still have to do an oxidation. So that would be a two-step reaction. Hydrolysis of a nitrile, which is C triple bond N, will produce a carboxylic acid group. Reduction of an aldehyde would take you back to an alcohol, which would require oxidation, and substitution of a haloalkane would also require a second step to take you to carboxylic acid. Therefore, B is the answer. Question 23. A student attempted to predict the mass spectrum of propanone. A predicted spectrum is shown below. The actual mass spectrum of propanone only contains 3 peaks. Which of the above peaks would not appear in the actual mass spectrum? So to do this, we need to draw out the structure of propanone. One of the peaks that you would see in a mass spectrum would be for the whole mass of this, would be the molecular ion. Now the whole mass of this would be 58, which would correspond with D. If we were then to start chopping this molecule up, we could then find the other 2 peaks that we might expect to see. If we were to chop here, we could end up with 2 ions. One ion, which could represent the methyl, which would be at 15. And then another ion, which would represent this other half of the molecule, which would be at mass 43. This means that we would not see B in the actual mass spectrum of a propanone. B would be for if the 2 methyl groups were to join together, which would not happen. Question 24. Analysis of a compound shows the following percentage composition by mass. The empirical formula for the compound is what? So if we take each of these to be the masses that are present, and then we divide by the relative atomic mass from the data book, we'll get the number of moles. And then dividing by the smallest, which is the oxygen here. And then rounding up where we don't have whole numbers, we can see that we should have C10, H14O, which would be A. Question 25. Which of the following splitting patterns would be observed for the circled atom in the high-resolution NMR spectrum of ethanol? So for this one, we need to look on the neighbouring carbon and see how many hydrogens it has. So the neighbouring carbon has 3 hydrogens. We then need to use the n+1 rule. So n equals the number of hydrogens on the neighbouring carbon, which is 3, plus 1 will give us 4, which is a quartet. Question 26. Pramipexole is a drug which is used to treat the symptoms of Parkinson's disease. Pramipexole acts like a natural compound in the body, dopamine, to stimulate the nerve cells. Buprenorphine is a drug which is used to treat heroin addiction. Buprenorphine stimulates receptors in the body but produces less of a response compared to heroin. Which line in the table best describes pramipexole and buprenorphine? If we look at pramipexole first, we can see that it acts like the natural compound in the body and stimulates nerve cells. This means that it's acting as an agonist, so we can ignore C and D. Buprenorphine also stimulates receptors but produces less of a response, but because it stimulates the receptors, this means it is also acting as an agonist. Therefore, A is the answer. Question 27. The human nose can generally detect the toxic gas hydrogen sulfide at levels of 0.03 parts per million. If a person inhales 6 litres of air per minute containing 0.03 parts per million of hydrogen sulfide, what mass of hydrogen sulfide is inhaled in 10 minutes? 0.03 parts per million is equal to 0.03 milligrams per kilogram. If we take 1 litre of air to equal 1 kilogram, then this would mean that for every kilogram of air, you would have 0.03 milligrams. In 1 minute, you are inhaling 6 kilograms of air, which would be 0.03 times 6, or 0.18 milligrams. In 10 minutes, you would therefore be inhaling 1.8 milligrams, which is D. Question 28. Which of the following techniques could be used to purify an impure sample of solid caffeine? Thin layer chromatography is used to work out if your sample is pure, but it isn't a purification technique. Heating under reflux is used for reactions to make things react over a longer period of time. Distillation is used as a separation technique of liquids, and recrystallization would be used to purify a solid such as caffeine. Question 29. When substance X is distributed between equal volumes of two immiscible solvents, water and dichloromethane, an equilibrium will be established, with some X dissolved in water and some dissolved in the dichloromethane, with a K value of 4. In the diagrams below, the number of dots represents the relative distribution of X in the two solvents. Water is less dense than dichloromethane. Which diagram shows the correct distribution? If water is less dense than dichloromethane, then it will float on top of dichloromethane, which means we can ignore A and B. We now need to turn our attention to K. K equals the concentration of X within the dichloromethane divided by the concentration of X in the water. And we can see that that equals 4. This is the equivalent to 4 over 1, which means we'll have more X within the dichloromethane than we do within the water. If we have a look at each of these diagrams, then we can see in C we have more of the X in water than we do dichloromethane, whereas in D it's the opposite way round. Therefore D is our final answer. Question 30. A complexometric titration can be used to determine the concentration of what? Complexometric titrations are used to look at the concentration of metal ions. Therefore, it would be used to find the concentration of calcium ions in milk. Thank you for watching my video. I hope that you found it helpful. Please remember to subscribe and ring the bell to be notified of new videos. You can also follow me on Twitter at MissAdamsChem and Instagram MissAdamsChemistry for updates on new videos and flashcards throughout the year. Bye for now!